I think the best idea is I did in opposite way. The first one is to remove the load first. So that one I have to be very careful. So let me show the results. So this is the data I recorded. Basically, the input voltage, this one, the output voltage, no load should be same, but it is decreasing as we increase the load. And also it is the current. Generally, we represent current with increasing load. So that is as we increase the current, that means as we increase the load, the current also increases. That is the we we tell electrical load increase, load in which we measure in terms of current. So this one is the current increasing there as the load increases, and then also the power is also increasing, you can see, and the angle also increase. So we will, what is the next step after that one? Plotting, drawing a plot, a graph between active power and reactive power. Active, draw a graph between active power and receiving end voltage. Okay, use total active x-axis, receiving end voltage, and y-axis. Receiving end voltage, okay, receiving end voltage on y-axis, total active power in x-axis. So in the graph, total active power, the x-axis, hopefully this one, receiving voltage. No, this is y-axis. This is x-axis. What is that? So you use total active power on x-axis. Total active power. X-axis total active power. This one. And then receiving end voltage on y-axis. So y-axis receiving end voltage. This is, so what happens here? This is the active power. As the power increases, what is happening? It is it's showing the output. The receiving end voltage is decreasing, kind of thing. It is not linearly decreasing. It's a little bit. There is a curve there. There is a curve there. So that's what we need to. It is not linearly decreasing, but there is some kind of curve is there. Okay, so that one I will record it. I think we have to snip and then mark, paste there. So I copied and pasted here the graph. So as the power increasing, the voltage is decreasing, but not linearly, but some with non-linear fashion, kind of thing. The next one is drawing another plot. So active power, that is also power and angle we will be measuring. So how they are related, we will see here. So instead of voltage, we'll see the angle here. So as the power increases there, and it is linearly increasing, kind of thing, but there is small, there is some curve also there. So that is what the curves. Let me copy and paste it. So that is the copied. So the power versus the angle here. So it's because of negative this fourth quadrant, we can see. So that is, I think, linearly decreasing at sub, but there is some non-linearity. We can see here also same thing maybe. So it may be linear for some time, but non-linearity coming to place. So the theory I will study more, I guess. So next one is connecting the DMM to measure the voltage drop in the transmission line. So locate an unused DMM and turn on it, set the voltage, AC voltage 200 volts setting, identify the voltage top red and black terminals, and then on the transmission line identify 1 and 4 terminals and connect that one between 1 and 4. Basically we are trying to measure for one phase. I think if you go to the circuit diagram here, circuit diagram, so 1 and 4 will be connecting an voltmeter between 1 and 4 to measure the voltage drop of one phase. Okay, but we are measuring the line voltages here. This one is the phase voltage. So what you have to do when you do the vector calculations or vector representations kind of thing, you should be converting that one, these voltages into phase voltage to check the validity of the numbers. So this is the hint I would like to give. So okay, so next yeah, we are here. Yeah, this is the step. We'll do it, and then we'll apply voltage, and then okay, capacitive load is also there. Okay, so we'll be using capacitive load to adjust the voltage profile, I guess. Let us see. But first we'll connect this one and then come back. So we'll apply 100% voltage and recording the data with capacitive load. In each step you need to record the value of capacitance added and the value of voltage from DMM. So this is the node, and node 2, maintain the balanced capacitors. That means for each phase you should be having the same value in each phase. What we noticed in the past, students, they are adding capacitance to one phase and then remaining they are not adding, just to see the balance. That is not the right way of adding the capacitance. We need to apply the balanced load, means each phase should be having the same value. And for each resistive load specified in table 3, we adjust the capacitance in each phase such a way that the voltage E3 is as close as to 208. That is the objective here. So and then each load setting record the value. So what happened, as you saw in the previous experiment, as we increase the load, the E3 was decreasing. So now by adding capacitance, we are trying to boost the voltage here at the secondary voltage up and matching with E1. E1 is the sending in voltage. So that is 208 volts we are expecting. So that is what we are trying to do. So this is the very interesting experiment, and in real life in power systems to improve the voltage profile at this receiving voltage, they also do the same use the same method. So this is the very important thing to note. Okay, so this is the DMM I will be using. So I will be turning on this, and voltage function I select. AC means it's pressed, and then 200 ohm volts, that is the setting. I will be using these two terminals there. So I will use what is that? I think white color, one white, one red I will use, or black maybe I will use, just to distinguish the different colors kind of thing. So this one I will use here, and I will use this one here. So this one I will connect. So that is the high potential terminal. I can connect anywhere, it doesn't matter, but just I'm connecting this one here, and I'm connecting this one here. So this is the voltmeter, will measure the between of one phase kind of thing, and we set that one turn on, and everything is fine now. So what I will do, I'll go back to the metering window, and then I will apply 5. I think I will erase the pre-volt data, and I will also put some voltage here. So I will properties, label, description. DMM. So so this is the DMM voltage. So I will be measuring manually here. So right now I apply 5%, no high current is there, and apply more 100%. So that's to apply 208, 208 volts is there. Right now it's no load is there. So what is the next step? So okay, for each load specified in table 3.1. So 3.1, if we go back, so that is the load. So first load is the no load. So for this no load, what is this? And we are supposed to maintain the, so E3 is same as E1, so there is no correction is required with the capacitor. So I will just take as is like this, and I think I have to record capacitor also, another capacitor. So I'll press C per phase, and then it's microfarads. So I will add this one also there. Okay, so that voltage is 0, around 0 there, and no capacitance is added. Oh, it's going there. So no capacitance is added, 0 capacitance. Okay. And the next load is I think 1200. No, here. Next load is crazy. Next load is 1200. So for 1200, and we'll see what is happening. So we'll apply 1200 here. And you can see that the voltage decreased, the E3 decreased from 208 to 205 here, and there is a power there. So now same condition like before. Now we are adding capacitance to see if to match the voltage. So if we add the lowest value 2.2 microfarads in each phase, so is it improving? So the voltage became 228. So it's very high. The difference is very high. That means the lowest capacitance we are adding, that is not improving. It's lower voltage we are getting. So that means there is no voltage increment is there. So we'll just record this value. But I will take the reading here, 11.76, 11.76 voltage, and then frequency capacitance is 0 capacitance added there. So the next one is I think 600. So 600, for 600 I will add 600 each phase. The voltage got increased there, that's correct. And then you can see the similar way there like last time. But now suppose if I add capacitance, so right now the voltage decreased to 200. If I add 2.2 microfarads, so will it improving? It's not improving. 222, it's too much overcompensation. So that is also not the good idea to have. So there is no capacitance required there, so we'll leave it there. And the voltage is first let me take the reading, and then we'll first let me take the reading. Oh, delete. So that is the reading, and 0 capacitance, and voltage is 23.93. 23.93, okay. And the next one is 400, that means 1200 and 600 in parallel. 1200 and 600 in parallel there. So I can see the voltage is down by 194.8. So if I add 2.2 each phase, is that improving? So 214 without this one, that means it's from 2.8, so it means it's 6 volts difference there. So this is giving 95, and then what is the difference? This one is 5 and so 11 volts. So that means I think by adding this one we are getting a little bit of over voltage, but the difference between the sending and receiving voltage is minimum in this case. So 207, 208, 14, there is a 6 volts difference there. In that other case it's more than 6 volts. So we'll take this one. So we will take the value, and the voltage is 40.22, 40.22, and then we are adding 2.2 microfarads in each per phase. So the next one is 400 we did. Next one is 300. 300, turn off this. I think we'll turn off this one also. And then 300 each one. So the voltage reduced to 186 there. The voltage reduced to 186. So if I add a capacitance of 2.2, so it's became 203. 203 and 207, that means they're very close. If I add more, will it improve further? It became 246. 246 is not acceptable, it's too high. So I will keep that 2.2 in that case. So I will take the recording first, and then 51.36, and then capacitance 2.2 microfarads I'm adding there, and then I will remove again now. So what is the next? My next load is what is my next load is 240. So 240 is 300 and 1200. 300 and 1200. 300, 1200. If I add this, so I got 178 volts at the receiving voltage. So if I add the capacitance 2.2, I'll start always from the minimum. So it's 193. It happened. So if I add 4.4, it is 129. So maybe if I remove 2 point, only have 4.4, so that is 210 and 207. So this is the closest. That means 4.4 microfarads will make the voltage 210. It's very close to the 207 or 228. So that is, I will take the reading here, and then I will 69.02, and then I will what happened here, 69.04, and then the 4.4 microfarads are added here. So my next load is 300 and 200, 300 and 600. So I will add 600 instead of 1200, and so the voltage, they will remove all the capacitors right now for the time being, and I can see 169 volts. It's very low voltage compared to the 209. So if I add 2.2, how much it is? 182 I'm getting. If I add 4.4 alone, I am getting 196. Maybe if I add 2.2 in parallel with 4.4, it's 211. 196 means 4 plus 8. 4 plus 8, that is 12 volts difference. Here it is 207 minus 211. It's how much it is? 1 watt. So 4 volts difference is there. So that means this is better than the previous, without having that one. So without having, if I have only 4.4, the difference is more than if I have 4.4 and 2.2 together, the difference is less. So I will take this one, and then I will just enter it. 86.3, 86.39, 86.39, and that is the, we added 2.2 and 4.4 capacitors. They get added when they are in parallel. So that is 6.6. And the next one is all the resistors in parallel. So I will add all the resistors parallel, and then see what is the, so with 96, that is I think 96 volts, 96 and 10 volts difference is there. 206 at the prime secondary, the sending end voltage. If I have 8.8, will it improve? Let us see. 164. Oh, sorry, 160. 200. Okay, that's very good. This is by having 8.8 microfarads, the voltage 207 it became. So that is good, that is very good, very close to the desired value. So I will take the reading here, and then you remember I missed this adding the resistance, so the voltage it was showing completely different value, so I got surprised. So then I realized all the three phase they have to be turned on. So that voltage 101.1, and then the capacitance I added 8.8. That means I think linearly it's increasing, I guess. They added the capacitance, so that is the thing. So let me show you the results now, and then we'll discuss that one. What is the next step? So once it is done, powering down, that's it, and then plotting. Okay, so what's first powering down? So to power down, so I'll just remove the load first, remove the load, and then turn off the power. So let me show you the results now. So this is the data I collected. So we applied around 208 volts here, and if you see here, the voltage profile got improved here. Before it was without any capacitance added, it was just changing from 207 to 161 there, 161 volts. But if you see the variation here, this variation is very less. So this is only possible by adding the capacitance here. So in some instances, the need of capacitance was not there because the load is light. The load is the power. What is the power here? This is the power here. The load is not, the power is not much there. But as the power increasing, then the voltage profile could be improved by adding the capacitance. And you can see that even though the voltage, sending in voltage is at here 207, and then receiving in voltage, let us consider this one 207, receiving voltage 206, around 206, but there is a difference. Even though the difference is not much here, but the different we will have a voltage drop. So that generally for a layman it surprises, but for the engineers like us, so it should not be surprising. These are phasors you need to deal with. So you can, I think there is a we need to prove why it is so something like that. It will, there is one question I guess you will not answer, but that is the, so by the way, this is the phase voltage. This is the phase voltage, these are the line voltages. So when you want to verify the results with phasor diagram kind of things, you need to convert them into phase voltage kind of thing. Okay. So then what is the next? We will draw a plot here. So again, active power and receiving voltage. So similar pattern we will be using. So we want, so that we can compare with capacitance, without capacitance, what is happening kind of thing. So the active power is there, and then this one we will, okay, so this is jumping up and down. Maybe I will insert 0 here. So that will, you can see that by inserting 0, the graph changes from 0 to 8. So if you see, the voltage is more or less constant. This is what the regulation is all about. Regulation means instead of letting the voltage to drop on its own, like previously, we are trying to regulate the voltage. We are trying to control the receiving voltage by adding the capacitances. That's what the thing. It's a very interesting experiment, I guess. Hopefully we'll just copy and put it down there. So this is the one I copied and pasted here. So the next one is graph, same thing, active power versus phase angle. So we'll just draw a phase angle, remove this, and this is phase angle. So you can see active power versus phase, no, not this one, I think this is, what is this? This one, this is phase angle. So it is linearly increasing now, and you can also, I think you can compare this graph with the previous graph maybe later. Okay, let me copy before the video is getting too long, so that it won't be truncated. So I will just paste it here, Control V, Control S. So that is the thing, and I think we are done with the experiment. I guess if you are here, you will be uploading into the learn Dropbox, data Dropbox, but it's not here. I will be uploading this data for you so that you can complete the report. And I think there's an insight here. You can this is very good insight. Maybe you can read it yourself, so that to avoid wasting time, I would be stopping here. So definitely, hopefully you learned something from this experiment. See you in the next lab then. Okay, bye bye.